So we are back with the last event of the day, but definitely not the least. It's about funding, right? So I have speakers with us. Let me quickly introduce them, and as the other panels, they're going to give a 10-minute talk, and we will have seat questions displayed. We will ask them questions, and we will get questions from you. So first on the right, Nadia El-Masry is a program director at NSF for the Engineering Research Centers in the Division of Engineering Education and Centers. El-Masry was a full professor of materials science and engineering at North Carolina State University since 1996. Her research field is in spin electronic material and devices for memory devices and semiconductor material and devices for light-emitting diodes and solar cells. Dr. Paul Hale is the Deputy Director of CHIPS R&D Metrology based in Boulder, Colorado. Yay! Prior to this role, Dr. Hale was the Chief of the RF Technology Division in NIST's Communication Technology Laboratory. Dr. Hale is a fellow of the IEEE and ex officio member of the International Electronics Manufacturing Initiative, the Board of Directors, a member of the Industrial Advisory Board for the EE Department at the Colorado School of Mines. Patricia Simmons is an NSF program officer in engineering education and research centers, working specifically in the engineering workforce development cluster. And you met her already in the yesterday's panel. She is a former professor at University of Georgia, University of Missouri St. Louis, and department head at North Carolina State University. Dr. Simmons is a Science and Technology Policy Fellow at the American Association for the Advancement of Science. Gilroy Vandentop is a VP of Intel Labs and the Director of Corporate University Research. His team manages Intel's university research investments for key internal technology and business customers. Gilroy is also on the board of the SRC. Before joining the board, Gilroy took an assignment at SRC as the executive director of the StarNet program, an earlier version of the SRC DARPA JUMP program. Kashyap Yellai has been with Semiconductor Research Corporation, SRC, for the past 2 years and has been leading a multitude of programs, including logic and memory devices, nanomanufacturing, materials and process and environment, safety and health research programs. Kashyap has 15 years of industry experience in research and development with new product introduction and technology ramp to mature yields. And we will start with El-Masry, so come on over. So, El-Masry, here, there you go. And we showed. Okay. Thank you.
Looks okay. Thank you, Mehmet. And first of all, I'd like to thank the organizing committee for inviting me to come here. And at the same time, you know, I have enjoyed all the talks, all the panels. It's very enlightening how everyone coming from a different sector, how his views or different opinion as far as semiconductors. And as you heard, I'm coming from the community of the semiconductors. And currently, I am a permanent program director at the Engineering Research Centers. Also, I am the co-chair of the FUSE programs, which is the Semiconductor Working Group at NSF. And also, I just got appointed to be on the working group for semiconductor workforce development at NSF. And at this point, I'd like to more or less remind everybody that semiconductors impact our life everywhere, whether it is telecommunication, whether it is healthcare, in the car, you know, computing, you know, energy. It's all, you know, affecting us as far as the semiconductor, and it's very critical for the US to regain leadership in that field. And that's not only for economic growth, but it's also for national security. Now, the CHIPS and Science Act has really empowered NSF in so many different domains. One of the domain is it's authorized a doubling of NSF budget over 5 years. And by the way, we haven't seen that yet, but it is, it's supposed to be doubling NSF budget. And also, it is strengthening the fundamental research. As far as NSF, it's not only the core programs that funds semiconductors, but there are so many different programs that's being initiated inside NSF to fund semiconductor. Also, it's established industry partnership, which is new for NSF. Yes, there is a previous 1 or 2 programs for industry partnership, but that is more or less the going culture, if I want to say, inside NSF to establish technology and innovation as far as the industry. Also, NSF invests in STEM education and workforce development, and of course, now we're going to target the semiconductor as far as workforce development. Also, we do at NSF is, advance diversity in STEM education, and at the same time, we are addressing the research security as far as the country is concerned. This is more or less, I'm having, in a way, few slides that really give the message. And the message here, which is telling us what is the NSF investment in that semiconductor domain. And actually, the NSF in general, it invests a lot of semiconductor. I myself, I was a program director in the electronic, photonic, and magnetic devices in ECCS, way before the CHIPS Act. And of course, a lot of funding went to the semiconductor domains. But currently, NSF is investing $350 million per year in so many different programs. And of course, the first program that comes to my mind is what I'm working on, which is the FUSE program. And the FUSE programs is investing in 2 rounds. Now, we had 1 round is already concluded and awarded, and the second round is on the streets. And both rounds adds up to $80 million invested in 2023 and 2024. That solicitation is based on the co-design approach for semiconductor and addressing, the stacking of materials, devices, and systems rather than, individual technology stack. Also, NSF, it invests in design, material, and engineering of the future, and we call it DEMREF in NSF. And it invests around $280 million. That's not 1 year only, but it's $280 million investment was in the semiconductor domain. The future manufacturing, this is an annual call for proposals, comes out from CMMI. And that is around $130 million per year. And I believe this year it went out with a call with a focus on also one of the components in that solicitation, excuse me, was about semiconductors. There are 5 national quantum leap challenge institutes funded by NSF. The total is $150 million. And each institute, which is considered a quantum center, would run for 5 years, and each year is like $5 million per center. And also the Engineering Research Center of the Center for Quantum Network, which is, this is the lead university for that center, and I'm the program manager for that center. And that's an investment over 10 years for between $55 and $60 million. The resilient and intelligent next generation systems that came from the Computer Science Directorate, which is SAIS, and that solicitation came out, and it's about it's a $40 million to enable emerging next generation wireless and mobile communication. Also, we are investing in National Artificial Intelligence Research Institutes, and everybody hears about the AI institutes, and that investment is around 500 million. It is the creation of new semiconductor technology in emerging industries such as AI, wireless, and quantum science and engineering. Also, in order to respond quickly to the CHIPS Act, NSF sent out several Dear Colleague letters, which is letters to request for the PIs to send and request supplements on their existing awards. And these supplements, it's about semiconductor fabrication and prototyping. And I'm going to tell you the acronyms, and we can more or less talk about what are these after whatever I'm talking about. So it is ASF, CMOS plus X, AST, and there is an ATF, which is in education. It's all targeting semiconductor. So I'm going to talk a little bit more about the FUSE solicitation, because there is one. Now the round 2 is on the street, and it is due on March 14. And so accordingly, I would like to talk about the two, FUSE 1 and FUSE 2, which is round 1 and round 2. The round 1 was 2023, and round 2 is 2024. The whole FUSE program is based on partnership with industry as far as funding and co-funding. So industry is co-funding that program with NSF. And for the FUSE 1 solicitation, there were 4 industry partners: Ericsson, IBM, Intel, and Samsung. And also for the FUSE 2 solicitation, this time we have also 4 partners. We added 1, and 1 dropped out. So we have Ericsson, Intel, Micron, and Samsung. And so what is FUSE about? FUSE is about co-design approach, research and development, exploring new materials and design for future devices and systems. Also, it has to have a strong education and workforce development based on interdisciplinary education and workforce development. Also, it encourages industry collaboration. But the industry that proposal or any proposal submitted should not be any of the 4 industry partners that co-funding. In other words, if you are collaborating with Intel, you're not supposed to have Intel on your proposal. So in a way, any industry can be a collaborator, but the 4 partners are co-funding. Therefore, it's very critical that we don't create a conflict of interest as far as these proposals. Now, the idea is based on the fact that NSF, engineering, SAIS, MPS, or EDU, they are working on the fact that most of the proposals funded are based on basic research, inspired research, proof of concept. And this is where it stops. And then if we look at what industry is looking for, they are looking for impact, societal impact, commercialization, and also product and solution development. And there is the value of the desk, or value of desk that TIP has been created at NSF to cross over that. And FUSE had the same concept as far as what kind of proposal we really would like to see in order to cross over the value of desk for the semiconductor technology. So it is based on the fact that we have 3 technology stacks: materials, devices, and systems. And the proposals has to choose 2 stacks in order to address specific topics or targets. Also, the topics, we have 3 topics. Topics based on research in domain-specific computing, and that's topic 1. Topic 2 is, well, let me reiterate here. Topic 1 goes to SAIS, computer science. Topic 2, it's based on advanced function and high performance by heterogeneous integration, and that goes to the engineering directorate. And topic 3 is based on developing new materials and energy efficient and enhanced performance and sustainable semiconductor-based systems. And the solicitation is based on having at least one topic and at least 2 material and device or system, one of the technology stacks. All of that has to be framed into education and workforce development component in the proposal. Okay, so we are talking about collaboration with industry, and therefore there will be the issue of IP. So how we are handling the IP at NSF, there is an MOU, Memorandum of Understanding, between NSF and any industry partner that co-funds, and these MOUs are based on the fact that any awards will grant non-exclusive, worldwide, paid-up, non-transferable, irrevocable, royalty-free license to all intellectual property rights under the funding agreement. And so, in a way, coming from academia, I know that institutions usually resist the fact that you give that more or less non-exclusive IP. However, the fact that a proposal reaches NSF, it means that the institution agrees on that condition. Now, all awardees will grant the license to each industry partner named in the award letter. So not all partners will be partners with any award, but for FUSE 1, Intel and Samsung were named as sponsoring parties on all awards. Now, for FUSE 1, Ericsson and IBM were sponsoring part of the awards. And so they were not on, they don't have the access to the IP for all the awards, but part of the awards that they select. But at the same time, the ones that they are not on it, they can connect with the PI and have some kind of agreement. The FUSE 2 has Intel, Micron, and Samsung named as the sponsoring parties of all awards, and Ericsson is named as sponsoring party for a partial set of the awards. And the reason for that, and everybody can realize it, that it depends on how much money these industry partners are putting in the solicitation. Post-award, so how the relationship between the industry and the PIs will be post the award. Well, they can offer contributions of resources, the industry partners, to any PI. Example, software, data sets, or computing infrastructure. And these awardees, they have the right to accept or deny the acceptance as far as what's being offered by the industry partners. Also, the partners have the right, not the right, but they can arrange for funds to one of their personnel, and it's like research in residence, that they can go to the PI lab and participate in the project. However, this is based on having the award institution, in other words, it's the university, has the right to refuse this setup. And it's not the PI. Again, NSF is funding. The institution is not funding the PIs per se. Also, the last thing is all reports, annual or final reports, after being submitted and accepted by the cognizant program officer from NSF, the industry partners have the right to see these reports. So some of the reports would have results that's not been published yet. So in a way, this is something that all PIs has to be aware of. Okay, so what happened is FUSE 1, first round, The budget was 40 million, but we were able to put up around 42 million, and we were able to fund 23 projects. On the average, it was a $2 million per grant. FUSE2, that is on the streets now, it is investing $40 million, and the anticipated funds would be 20 projects funded of collaborative proposals, and every project will be up to $2 million per grant. Of course, number of awards, and it can be up more than 20 or can be less than 20. It depends on so many different parameters and factors at NSF. If anyone would like to more or less have questions and send us emails about your question, you can contact fuse1@nsf.gov. That's the email that all program officers included in that solicitation. One of us will be responding to your email. And of course, all what you have to do to find the solicitation is type or NSF 24-521. That's all what you have to do to find the solicitation. We had a webinar on that solicitation, and it's posted on the website of the solicitation, and all the slides are there, and also a video of the webinar is on the website. Okay, I would like to thank you all for listening to me, and if you have any questions, I would be happy to answer.
Thank you, Nadia. So next is Paul. Let me quickly pull up your slides, which is going to be here.
Okay. Thank you very much. So, as always happens with a lot of money, there's a lot of disclaimers here. Just basically, everything I might be saying is going to be pre-decisional and preliminary in nature. It does not constitute a commitment by NIST, and is subject in entirety to any final action by NIST or the Department of Commerce. Nothing in this presentation is intended to contradict any of the published future policy documents or notices of funding opportunities. So, as most of you know, the CHIPS for America programs come in two parts, totaling about $50 billion, that's with a B. The first part, and $39 billion, is for manufacturing incentives, firstly to attract large-scale investments in advanced technologies, such as leading-edge logic and memory, and also to incentivize expansion of manufacturing capacity for mature and other types of semiconductors, as well as supply chain manufacturing. The remaining $11 billion is for research and development. This is constituted by 4 integrated programs, which I'll be talking about more on the next few slides. These are to conduct research and prototyping of advanced semiconductor technology, strengthen semiconductor advanced test, assembly, and packaging, and enable advancements in measurement science, standards, material characterization, instrumentation, testing, and manufacturing. Along with that investment at the Department of Commerce, there's also CHIPS initiatives from other agencies, including the DoD, Department of State, NSF, as mentioned previously, and Treasury. So how did we get here? Congress created a set of programs aimed at restoring U.S. leadership in semiconductor manufacturing and restoring growth in the microelectronics and semiconductor R&D ecosystem. This CHIPS strategy is informed by extensive engagement with semiconductor industry leaders and stakeholders across all fields, and NIST was selected as the bureau within the Department of Commerce to house these new units. So the vision of CHIPS is to create a vibrant and self-sustaining U.S. domestic semiconductor ecosystem. with the mission of accelerating the development and commercial deployment of foundational semiconductor technologies by establishing, connecting, and providing access to domestic tools, resources, workforce, and facilities, with the goals down the road by the end of the decade of creating U.S. technology leadership, accelerating ideas to market, and a robust semiconductor workforce. This last part's been the theme of the meeting the past couple days. So I'm with the Metrology program in CHIPS, which is really the core of the R&D program, and we expect to be working with all the other parts of the R&D program, including the NSTC, Manufacturing USA Institute, and the National Advanced Packaging and Manufacturing Program. Industry input is key, and in the spring of 2022, NIST held a number of workshops, a number of one-on-one interviews with industry representatives, and we created this strategic opportunities document that you see here, and you can get the link here is shown with the QR code. And this document outlines 7 grand challenges that we saw as being critical for advancing the U.S. semiconductor industry. So these seven grand challenges tie in to the semiconductor manufacturing value chain like this. So first of all, grand challenge number 1 looks at materials purity, properties, and provenance, establishing measurements to quantify those aspects of materials. Grand challenge number 4 focuses on modeling and simulating semiconductor materials, devices, and components, including packaging and mask design. Of course, having measurements to inform PDKs, for example, is critical in the manufacturing process and design. In the manufacturing process itself, modeling and simulating semiconductor manufacturing processes are critical. And as you all know, deposition, lithography, and etch are repeated many, many times to create today's complicated integrated circuits. And after each loop through these process steps, various metrology tools are required. So grand challenge number 2 includes or focuses on inline metrology tools. Finally, once you've got an integrated circuit fabricated, it needs to be tested and packaged. So grand challenge 3 focuses on metrology for advanced packaging and test after the wafer's diced. And then there's 2 cross-cutting grand challenges that need to be considered at all steps of the manufacturing value chain, including standardization of new materials and processes and equipment, and security and provenance, which nowadays is sometimes an afterthought in the design process, but needs to be included from the very beginning in the design tools. So CHIPS metrology, what's the status right now? So CHIPS metrology is funding a number of internal programs inside NIST. We've distributed $109 million in funding so far in 29 approved research projects over 3 of the grand challenges. Grand Challenge 2 has 10 projects funded, Grand Challenge 3 with 6 projects, and Grand Challenge 4 with 13 projects. You can find more information on the specific projects that have been funded by going to chips.gov and looking at the link on the left called webinars. We had a webinar on CHIPS metrology recently that gave the titles of all these funded projects and some short lightning talks on I think 4 of the projects. So these current projects are helping to develop new measurement instruments, measurement methods, and measurement-informed models and simulations for microelectronics design and manufacturing. This is about a third of the total funding for NIST metrology, so we expect that additional projects and the other grand challenges will be selected by the end of the year. Research teams have proposed several distinct industry collaborators to provide materials and software and conduct joint research with the NIST researchers, and we're expecting several collaborations with U.S. Universities, consortiums, research institutes, and various industry partners. So as I mentioned, interaction with industry is critical. Metrology is foundational and fundamental for all CHIPS R&D. Metrology solutions are delivered, must be delivered to industry stakeholders for us to be successful. High impact research areas were sourced from industry to put together our goals, and metrology, so that one of the main goals here is that metrology technologies should reach commercial scale, transitioning out of the NIST labs. So you can engage with the CHIPS metrology program by going to chips.gov and joining our email list. We'll be having communities of practice that will be starting in the next 6 to 8 weeks. And we're expecting that the members of this semiconductor space will have a chance to join with webinars, in-person poster sessions, networking sessions, and various symposia. And so this will be an opportunity to share knowledge with other stakeholders and learn about what other projects are being worked on. One of the things that came up early in our thinking about CHIPS was the need for exchanging data. And frankly, every place I go over the past several years, exchange of data has been critical. So we've been setting up the Metrology Exchange to Innovate in Semiconductors, or METIS, which is a data exchange ecosystem which is being developed by NIST, which will give stakeholders access to CHIPS metrology results and make that data available. So although the time to provide feedback on the METIS framework is just passed, you can still go to the website here and look at what NIST is planning on doing in that space, and look for other opportunities in areas such as digital twins for data transfer in the near future. Also, NIST Metrology has a number of postdoc level positions available. Right now we have upwards of 20 positions. We're looking for postdoctoral researchers right now. So you can go to this website and send in your application there. And we have positions in areas such as electron tomography, atom probe tomography, EUV scatterometry, scanning transmission electron microscope measurements, and that sort of thing. So that concludes my talk. Thank you.
is Patricia.
Okay, thank you. Again, it's delightful to join you this afternoon. So I thought I would take more of an approach that was one of the 35,000-foot approach as opposed to getting up close and personal. I think Nadia did an excellent job at communicating what is currently available from the NSF perspective, and Paul did an excellent job also talking to you about the CHIPS Act. So I'm not going to go into any details on that because I can't follow them. You know, they always say don't follow anybody who's better than you doing that. So they did an excellent job. So that brings us to looking at how can NSF engineering programs in particular address these takeaways that we've been hearing about during this meeting. So for example, one of the things that we can do certainly, and you heard this mentioned in the previous speakers, is provide access to fabrication testing facilities, test beds in academia and industry. And this is coupled, of course, with research infrastructure and instrumentation. The next chunk, if you will, that we can do in terms of addressing these takeaways is improving and innovating in engineering education. We've talked about that. We've talked about supporting broadening participation, what we can do to really create a more active pipeline for people to pursue careers at all levels, especially in the semiconductor sector, and then provide undergraduate research experiences. Again, I shared that with you yesterday, so I'm not going to go into any details there. But also we can provide opportunities for fellowships, for graduate students, postdocs, those currently exist. And then as you have mentioned previously, and several speakers have mentioned about the engineering students' internships within industry. And then very important, I think, and we do need to pay special attention to this, the mentoring and community building aspect for students, faculty, and professionals within the semiconductor research sector. It is critical as we move forward in this next 10 to 20 years for us to be quite aware of how we are going to go about doing that. And in order to be successful in the long term and provide national leadership, you have to have that community built that will support students, faculty, and professionals at all levels. One of the challenges, again, we talked about this a little bit yesterday, and we've been hearing about the shortage of engineers, especially in electrical and computer areas. There are a number of challenges to growing the number of engineers. We've been dealing with that at NSF, thinking about what is it we can do, what kinds of things can we do at a very local level that will help, but also what can we do nationally to address this issue. And again, you know, it comes down to the fact of attracting and retaining students. Again, a lot of students may start out saying, oh, I'm interested in the tech sector, I'll try that out, maybe semiconductors, but we can't just get them in the door. You have to help them close the door behind them and look at that as a potential and fulfilling career. So we need to pay attention especially to retaining students as opposed to losing them along the pipeline. Obviously, that requires infrastructure that needs to be supported for instruction, and we've heard about that already, and also curriculum has been mentioned certainly in the conversations yesterday. And again, I will come back to curriculum in terms of, in particular, compliance with ABET, because that is our main curriculum accreditation that we use in engineering to validate the programs and to ensure that we're meeting a very high standard of professionalism. So engineering takeaways, what can we do if we look more specifically at workforce programs? Engage the community and especially engage with us in the engineering directorate. You know, we value your voices at all levels. We enjoy talking with industry people, with our academic colleagues, with students. It's important for you to be in good communication with us so we listen to the community and what the community is telling us that you need. The other thing is we need to, again, as I've mentioned before, attract diverse students to this field and retain them. That is critical if we're going to move the needle forward. The other thing, I've talked a bit about teaching infrastructure. We have to go beyond the industry fab labs, so to speak. We need to think at a much larger scale about what will it take to sustain this type of development so that it becomes a permanent part of the economic sector and it doesn't go away in 10 years' time. And then lastly, the growth in pedagogical capacity and how we address that through various educational reform acts and also through the workforce programs. So I am delighted to discuss this further with you and welcome your conversations and questions as we discuss this in panel. Thank you.
Thank you very much, Patricia. So next is Gilroy.
Thank you. So I'm in charge of corporate university research for Intel Corporation. So I'm going to try to quite quickly give you a sort of summary of how we do university research and work with government and academia. We work in almost all the things we do are in combination with academia, government partnerships, and also industry partners. Just to describe sort of the areas of focus, my group is actually in Intel Labs. Uyghur spoke earlier yesterday, and he's part of components research. So Intel has kind of two research groups, one that's more at the bottom of the stack, and I just have that here beyond CMOS, heterogeneous integration. They do a lot more, but my group happens to be in Intel Labs, and that's more at the top of the stack. So we look at next generation connectivity, like we're part of the Rings and Fuse programs, emerging workloads. We have a separate group on security. We have a separate group on quantum, and obviously a lot of activity on AI. So just what you would expect. It's a pretty broad research portfolio internally, and then we extend that externally. This is just shows all the sites we have worldwide. We have, say, when I started this job in university research, most of our focus was around the research content and the tech transfer of research results. But recently, we've sort of pivoted and started putting more attention on workforce development. It's always been a number 2 priority, but I think right now we've pivoted to make it our number 1 priority. So we're investing in curriculum that we take from inside the company or build inside the company, share with universities, use it, participate in faculty training, do internships. I mean, we want to increase all of these things. We started doing equipment donations again. We had stopped that for a number of years. And I'm also responsible for the university shuttle program, and that's really a way to allow academics to participate in our multi-project wafers and be able to build some of their designs on our process. Like I said, we are investing more in workforce development. We're building new factories in Phoenix, in Ohio. So we started up a mindshare program for workforce development. A lot of that is focused in Ohio, but a lot of it is spread across the country. We've really built our partnership with NSF, and we've been partnering on a number of larger programs, both in Ohio and across, more open across the United States. And so I'll be happy to take questions later on. That's kind of a very quick description of how we engage with academia and government partnerships. Thank you.
Right, our final speaker is going to be Kashyap.
Hello, everyone, and thanks for staying till the end. And I'm Kashyap Yellai. I'm the science director from SRC, and I think the workshop got kicked off with Todd talking about SRC, and I'm wrapping up. So, if nothing else, you walk out with SRC. So that should be the theme of this workshop, rather than 1D, 2D material. So, anyway, all right. So. There was a quick intro, so I won't spend too much time on the slide, but one thing just want to highlight in my career is that I've been the far most end of the R&D pipeline that we've been talking about. All the while, I was the manufacturer I made thousands of wafers and dies and millions of dies, so I know the pain at the end after all this paint's been taken and turned into a nice product. It comes into my hands to ramp up the yield and make them cheaper. So that's my background, just in case you hear a different perspective. That's where I'm coming from. All right, so Todd talked about this in detail yesterday. So a recap for those who have attended yesterday, and probably a new content for people who are just joining in. So it's SRC is a consortium, research consortium. We do about $100 million research with about 22 staff. A lot of people had questions on, how big is SRC there? Their presence is pretty much felt everywhere. So we are staff of 22 people. We are based in Raleigh, North Carolina. And yeah, we manage about $100 million research. And the members on the slide are both corporate members and also from government. And what do we do? So in general, we don't have any research facilities. We facilitate research. We manage the collaboration between the government, industry, and the academia. So it's a member-based program. So we collect the dues from the members, and then we run solicitation based on the needs for the semiconductor industry, and then fund individual professors as an individual project or a clustered centers. And that's precisely what has been the model for the past 40 years. And again, you've seen the slide yesterday, so I won't talk much about it, but just want to highlight on few things that came out of SRC. Nanosheets for gate-all-around transistors, FinFET, when they first came about 10 years ago, high-K dielectrics for interconnects, right? So pretty much whatever semiconductor breakthrough we have seen has a presence in SRC in form of research from academia. So with that, what are the two main programs as such in SRC? Our Jump 2.0, which is SRC Co., which is in collaboration with government and industry, and then the other one is Global Research Collaboration, which we refer to as GRC. It is purely companies-based programs, funded programs. So Jump has started last year, and there are no active solicitations upcoming for Jump, so that program runs for 5 years, and it has a different operating model. It's a center-based, and universities lead there are primary universities that lead the centers. On the other hand, Global Research Collaboration, which is GRC, is purely company-sponsored research, and we have solicitations every year. So there are 8 programs in this, 8 research programs under GRC, and out of which at least 5 of them will have an active solicitation every year. And that's what I'll be talking about in the next few slides. And here is a quick snapshot on what are the programs, but we can spend some more details. And primarily we're funding 2 professors from University of Arizona, Professor Mutlu and Professor Takashima. And in addition, there are 3 co-PIs in Mutlu's group, Professor Komi, Professor Belviranli, and Professor Close, right? And there were questions on, does SRC, welcome new professors, young PIs, right? So I quickly ran research, and yes, in the past 3 years itself, we had 9 new PIs coming into SRC. So yes, we are open to new PIs. And these 9 PIs are along various stages of their career, mostly young and new PIs starting their career. So definitely that's the type of talent we would want in our portfolio. And then, so that's the programs. So talked about 3 Ps in general, and how we use these 3 Ps to guide our research agenda is what I'm going to talk in the next slide. So one's prosperity, people and planets. I thought refer to them in a different perspective, but taking that and internalizing within SRC and how does that look in our agenda when we call for research is starting with the prosperity. On the left, you see the 5 seismic shifts, which were called in decadal plan, will be the guidance, the what, right, and how much needs to be spent on each seismic shift. And then the map roadmap, which got released the last year, will be the 11 chapters, will be the research needs. So in the call coming up this year, you will be seeing references to the decadal plan and the chapters, maybe a chapter 4 for our materials call. So that will be the research needs. So all our research will be driven based on these 2 documents, and the PIs are more than welcome to get a head start, go through those documents, and see what's the relevant area under which your project falls in, right? So if we take those 11 chapters and classify into our 8 programs we have today, which we call the GRC research programs, they fall under these 8 programs, which is LMD, logic and memory devices. So I put a small brief introduction for each program, just to give you an idea, but the bottom link gives you more elaborate details on the programs. If not, you can always reach out to me and the rest of the program managers, which are listed in here in the slides. So what's coming up? So we have 5 research programs coming up for solicitation, and the link is the bottom, and then the link will become active for you to start submitting applications on those particular dates. So hardware security is coming on the 9th April, and the Nanomanufacturing materials and processes on 9th April. And the other 3 are coming on 7th May, the CAT-T, ESH, and packaging. Right, so they will run for approximately a month. They will be open. And the award size goes from 105,000 per year to 135,000, and also 150,000, which Rod referred in his Q&A. We changed. We went up from 87,000 a year last year to 105 and 135 and 150. So 150,000 is for logic and memory devices. We understand the clean room cost, and definitely we try to factor in there. And that's the only program that's getting 150,000. And obviously that's followed by materials research, which needs, again, clean room and testing of the devices. So that falls under 135,000. But again, we're making incremental progress in the award sizes. We definitely understand that this can still grow higher, and we're looking for avenues to build on those. Once we get those calls, and the call goes in 2 stages. One is white paper stage, which is we request PIs to submit just 1 pager on the research idea, and then once that's rated based on these 5 categories. One is obviously the ingenuity and novelty, and the broadening participation in talent development. So don't feel shy, even though it's 1 page. If that's the meat of the 1 pager, please add in there, because that's what we've seen so far is going to be the key for semiconductors. So please don't shy out on that particular topic. And support of SRC's commitment to sustainability. Obviously, that's another. So this is again coming from our 3 Ps. This is what our research agenda is going to be tailored on. And obviously the capabilities of the researcher and then overall scientific merit, right? So the next, all those 1-page white papers that gets invited for a proposal, that's a full-length proposal, goes for a 5-page proposal request. And again, it will be rated by SRC and the member companies, and then you'll be funded for 3 years according to, based on the GRC program. So that's about what I have upcoming. And
all right, so I'm going to pull up the questions we ask, and I think most of those questions are answered Thanks for the speakers. So I'm gonna, and please come forward, feel free to ask questions. If not, I'm gonna ask a sort of a ignited question. You have a question? Yeah.
Okay, she grabbed him first, sorry. I have the question for Nadia. So in the NSF semiconductor initiatives, there are a bunch of proposals which have been funded and I think going to be funded. Among all those proposals, is there any plan for something specific towards the early career PIs? And in the previously funded projects, how much, or what is the rough percentage that the early career PIs got those?
Well, number one question is about early career. That program, if you're talking about the FUSE program, is not really dedicated to early career. It is dedicated to the whole community. And it's based on forming teams, and these teams would address specific challenges and goals in the 3 topic areas. Your second question about the percentage success rate for the FUSE 1 round, it is a typical NSF success rate. So, and I don't think I am at liberty to really release the number, but I know the number anyway, so.
Hello, everyone. So Salahi, Assistant Professor, EC, University of Arizona. My first question is about the classroom tape-out that you mentioned that Intel does. And, I teach digital VLSI design, and, it's a challenge. I brought it up in my class that we have a clean room, and the students were very excited. So Zafar actually arranged a tour for the students in my class, the digital VLSI, to go and see what's a clean room. And that was a really great experience for them, and they couldn't stop talking about it. So we do want to give them more opportunities, right? So I know that UC Berkeley does this through their Chipyard project. They do some fabrications with Intel. Would you mind, commenting on that? How